Hello everyone. So today we are here in our fourth part of the operating system internals. In our first three part of this series, we have covered all the details around the process execution, what is the process execution model, how the detail of the heap memory, stack memory, context switching, uh, when exactly stack memory will be used in the different execution cycle, what is stack frame, all those details we have covered in our first three parts. And now this part onwards we are going to move into memory. So now the process part is over, we are going to go to the memory part. Before delving into the details, let's have a very fundamental misconception gets cleared, that is what exactly is a memory. So when we say like what is memory, we have to understand when we are talking about the memory, we are mostly generally talking about the RAM or the cache element of our operating system, not the HDD or the SSD. Okay, so HDD or the SSD, these are our storage, and RAM or the cache, these are our memory. So this goes to storage and RAM and cache goes to the memory. So although oftentimes interchangeably we mention that hard disk as a permanent memory and RAM as a transient memory, but conceptually from the fundamental computer science concepts, memory is the place which is being used during our program and process execution. Okay, so always remember, whenever a program runs, if you have seen the previous three videos diligently, one thing probably is etched on your into your mind right now, that is the place memory is the place where program or the process execution happens. Okay, and this is for the hard disk or the SSD used for the storage. So any program that we run, it is always run in our RAM, cache, and the CPU pipeline, whatnot. So we will go into all those details gradually into this series. But anyway, let's get this conception cleared one time for sure. Okay, so now let's take our general purpose laptop or desktop. They have the mix of two kind of RAM. One is the static RAM, another one is dynamic RAM. So when we are talking about the memory, so memory or the RAM, they have two very important components. Okay, one is called static RAM and dynamic RAM. So like the RAM, it has two different segregation over here. And when we are talking about the static RAM, so what exactly are the static RAM things are? So in case in your CPU box you have seen things like L1, L2 and L3 cache. Those cache are being termed as the static RAM, and where we are actually talking about like our RAM memory, that is the dynamic RAM. Okay, or rather I can say like the main memory system, that is being called as our dynamic RAM. Now static RAM is of course way more expensive than DRAM. And static RAM, what happens is during any execution, whatever the things are there in a static RAM, in a sub nanosecond latency, in sub nanosecond latency, it can be retrieved from there. Okay, so it is very fast. So anything that comes into the static RAM, it is like in a sub millisecond, in a sub nanosecond latency, and in sub nanosecond latency it can be retrieved. And for the DRAM or the dynamic RAM, it can be retrieved in a nanosecond latency. Okay, so when I say sub nanosecond, means maybe something around like the zero point 0.5 nanosecond, and probably for this one generally it is like 2 nanosecond. uh, that much amount of time will be required to retrieve it. And now again guys, this might change because the way the computation is moving, 10 years down the line, these things might be way more lesser, like this can be 0.05 nanosecond. Okay, so now coming into this, one question might be bugging in your mind that how come SRAM is so fast and DRAM is not that fast. So that, although that is a very, that will open up a very interesting discussion, but that is not exactly our point of interest right now. So just understand one of the chip based or the electrical details, which is again not very important for the computer science engineers or especially for the developers for this particular scope uh, in which we are discussing this whole internals. So the flip flop is being used to design SRAM, whereas for DRAM we use capacitor. Okay, so SRAM is flip-flop based and DRAM is capacitor based. That is why SRAM is designed to be very faster, and of course this is a way more expensive one. And if there is a like a 16 GB or a 32 GB of main memory available, SRAM we will see in few MBs. So that is why the L1 and L2 and L3 cache, they are very expensive and completely controlled by the operating system, and we will see how data goes into the SRAM and DRAM, and they are being exchanged among these two part in our use cases, especially like when we will see that this real world example. Okay, so now coming into one simple example at first to understand the memory layout. Okay, to understand memory layout, let's deep dive how a request being served from memory perspective by a server. So again, just taking a cue from my previous videos, if you have seen those ones, you have seen that multiple places I have covered how exactly a request being served by the operating system. Suppose there is a server in which from a client machine one web server request comes. Okay, this is a server and there is a process, there is a web server process running. Okay, there is a web server process running. How exactly this is being served to the client, that we have discussed earlier from the process perspective. Okay, so process perspective, we already know what exactly happens, like how the stack frames and the other things comes in place. So now instead of process, we are going to explore in the memory perspective what happens in OS. So then when we bring these two things together, lot of other peripheral concept will be crystal clear to us. Okay, so now let me come to a box diagram how it exactly happens. Okay, so I have made the very basic diagram. Suppose this is the machine over here, all this block, and this is suppose our web server machine. And in this web server machine, what are the things we have? We have a NIC card, that is a network interface card. We have our operating system kernel, the web service, the web server process that are going on, and then there is the DRAM. There is something called TLB, which we will definitely discuss later, and that is the cache or the SRAM. So let's take it from that vanilla example. Like there is a endpoint of get user 123. Okay, so once this get user 123 comes into the NIC card, what NIC card does is it tells the DRAM that one packet has arrived. Okay, so all these components I haven't linked them together yet, but it happens like this. If you keep on noting it, it will be very easy for you because the diagram is going to be a bit messy. Okay, so this NIC is going to tell the DRAM that look, I have a packet for you. Okay, and this packet you need to process. So the moment this part is being done, so this is the first part. Okay, this is the one. So the moment this part is being done, this writing is completed to the DRAM, what NIC card then does is it sends an interrupt to the kernel. What is an interrupt? Interrupt is nothing but a signal. Okay, interrupt is nothing but a signal. What this signal does is interrupt signal. I will just write it there. Interrupt signal is being sent to kernel, and what it will tell to kernel that look, there is some data I have placed in my DRAM buffer. Okay, so again this thing is being called there is an interesting name to it. It is called descriptor ring. So ring means like a ring buffer. The data will be kept there, and it will be get processed uh, for later purposes. Okay, so this descript sorry not description descriptor ring. Okay, so this descriptor ring will be available now, and now also the kernel knows that okay, for me, that this descriptor ring I have to get the data from. So now what this kernel does is, as the third step, it goes there. Okay, it goes into the descriptor ring. It goes to the descriptor ring, and this is the third third step of this. Okay, now again, just to revise, from NIC card has placed the data to the descriptor ring, and kernel is being informed via interrupt, and as a third step, kernel will go to the descriptor ring, and it will tell ki I will now start processing. So then couple of thing happens, like it will mark this socket as readable, and this read operation will be initiated, which is not very important in terms of operating system internals, but that goes into more on a network side. But just understand this thing, now kernel is able to read it. Okay, so now what kernel does is, now kernel for this processing goes to TLB, or the translation look aside buffer. So it so after it gets the descriptor ring, now what it will do is it will go to the TLB. Now kernel has the data, now it will go to the TLB, and TLB will tell ki what exactly the web server process and in what memory address uh, it can go and take or execute the certain instructions. So now that we have TLB, so TLB, I'm just writing the full form here. It is translation look aside buffer. It is a very important concept. So what TLB does is, so ideally, translation look-aside buffer, or the TLB, it holds the latest virtual memory address pages which are to be processed. So in case there is a TLB miss, it goes to the MMU. But just for the time being, understand this part, that our kernel, what it will do is, from the TLB or the MMU, okay, from the TLB or the MMU, it will try to find out where it would take the request forward. And now the TLB will tell ki now you can take that request forward to this web server process with this read request. So now TLB tells ki after like 4 onwards, okay, so after 4 TLB tells you take this request to this host, to this to this application host. So this web server process is basically our application host over here. Okay, to this application host. Now from TLB it will go here. After getting the data from TLB, kernel will go here, actually not directly from TLB. After getting the data from TLB, kernel will go here in the web server process. So now what exactly is happening over there is, kernel is taking the data from DRAM, it goes to the TLB as a to understand where exactly it would go and execute this particular process. And then what would happen is, in case TLB miss happens, it will go to the MMU, and after that it gets the actual address of the web server process or the host process, and from there, once this application process request is done, so this is the 5. Okay, the diagram is become messier, so 6 onwards I am going to write it outside. So 6 onwards, what happens is, application process the request, then response is written to an output buffer. So in this process, after this processing, what happens over here is, web server takes the data and place it to the cache. Okay, so application processes the request and the response is written to cache, and from there it goes to the output buffer. So output buffer is nothing but a send buffer, and there what happens is, kernel then copies this data from this cache to this output buffer, and then from this output buffer, from the output buffer, data is being sent back to the NIC, and NIC then take it to the client. So this is again a long process. Let's understand it again. So once this request comes, I think this part is quite clear that it comes to the NIC card, and from that NIC card, it initially it puts the data into the DRAM, and after, as a first step, and then as a second step, it creates an interrupt to the kernel, and now the kernel knows that there is in my descriptor ring something is sitting to be processed. So what kernel does is, kernel will take this data and then it will go to the TLB or the MMU. TLB is the translation look aside buffer, or the MMU is the memory management unit. From the TLB or the MMU, it tries to find out what is the next address space it should go to execute this process, and then it see that, okay, this is my web server process where I should be running it. So now what happens is, application then generates the certain response. So from that response, it uh, is initially into that particular application space, and then it will be placed into that uh, placed into our cache. Like when I say cache, means L1, L2, L3 cache, or the static RAM that we were talking about. Okay, and after that static RAM, it will be placed into the DRAM. It will be placed into the DRAM, and then what kernel will do is, kernel will take this data and it will put into the kernel space memory, and this buffer, this buffer that we are seeing, this output buffer, will be then transferred to the NIC or the network interface. Okay, so now my network interface knows that there is something in my output buffer. So initially the network interface card, whenever it got the data in its input buffer or the accept buffer, it writes it to the DRAM. Now what it will do is, now the output buffer knows, uh, now the NIC node knows that whatever is there in the output buffer, it has to send it back to the client. So what it does is, it will add a few of the policy related things, like for example, from which IP address it is sending the response back, and some other details. And what it will do is, it will then offload it to the client, and the client will receive the data. So this is the complete memory layout that we got over here. And one of the two very important concept we touched upon is like how DRAM and SRAM comes in play. So as you understood, like whenever a response is created, at first it will always will go to the cache, then it will come to the actual memory, and from memory it will go to the output buffer. Now one more important concept we didn't touch upon purposefully over here is the concept of DMA or the direct memory access. So where does DMA or the direct memory access comes in? We will discuss in detail now. So why we just skipped, because it would have complicated our whole discussion a lot, so I just skipped it there. So understand one thing, that when NIC receives a packet, if we are aware that any of this data has to be present into the memory, even if it is like some kind of a hard disk or the SSD data, all of our memory has to be put into the DRAM. So the postulate that I am trying to establish is any data that comes in NIC, unless we place it in DRAM or main memory, we will not be able to process that. Because if you remember, at first when we started our discussion, we told that memory is the place where the program and the process execution happens. So unless something is there in my memory, how come the other components of my operating system would know that this is something that is to be processed? Okay, now this request before processing will be need to be placed into the DRAM. Now this is the question, like how this is done internally. So here is a very important concept of DMA comes in place, how this copy of data happens. If we understand how this copy of data happens, we will understand what DMA is. So let's understand that. So when a packet arrives at network interface card, it needs to be stored somewhere, right? It needs to be stored somewhere so that the kernel or the application can process it later. Now, if the CPU had to copy every byte from NIC to memory, now who will copy it? The copy of NIC to DRAM, is it the CPU does? So CPU, probably by now you understand, can a certain CPU core can only do a single instruction at a one point of time. So the moment my web server will be hit, if it is a CPU's responsibility, my CPU will be busy. Okay, and what will happen internally is my CPU will be completely busy in handling those calls only, because suppose there is a web server which is serving maybe 20,000 records per second. Okay, so that much amount of processing CPU will be busy. Now this will like asking a top engineer to do some manual labor, right? Like CPU is meant for some better execution. So instead DMA comes over here, or direct memory access. Okay, so what does DMA do? So DMA, let's have the functionality at first. Let's the NIC write directly to DRAM, bypassing CPU to be involved in copy step. Please understand it very diligently. So there is no CPU involvement in this process. Internally, the kernel sets up the memory buffer in main memory. So in my main memory, so if I just write it like this is my main memory. In my main memory, there will be a buffer that is always being maintained. Okay, kernel sets up this memory buffer, and this memory buffers that are the information shared with NIC via the DMA descriptors. Okay, so NIC, what does it have? So if I write NIC over here, NIC, NIC have a built-in DMA engine which keeps on track of the free buffer of my main memory. Okay, so what it does is those memory buffers informations are totally completely shared with NIC via this DMA descriptors on, and this NIC's built-in DMA engine takes the control of the system bus. So again, going into a little bit on hardware part, so the PCI or the system buses, they will comes in play here, and what it will do is any data that are sitting, okay, any data that we get at the NIC from the client end, this data will be transferred here. Okay, this data will be transferred here by the PCI or the system buses, and these packets are directly written into this specified memory address of the buffer. So CPU doesn't, what is the advantage of this process is CPU doesn't have to get involved in this whole process, doesn't have to get involved here. Rather, DMA engine and DMA descriptor does the magic. Okay. Now what happens after this write is getting completed? So now probably you understand this part 1 in very detail, that who takes the data and how it is being copied. Okay, so this part of the memory, I hope it is clear now. Now let's take it from here. What happens after this? After this part 1 is being done, then we discussed there, right? Like once this buffer copy is completed, the kernel, the CPU sends a interrupt to the kernel, and kernel handles the interrupt and finds where the packet was written into the memory, and then gradually processes it. So after DMA comes in play, so then only this interrupt will be sent. And also, while we are sending back the data, so when the data is in output buffer, uh, where exactly, when we are putting the data into the output buffer, where exactly this data we are going to put, that is also controlled by the DMA only. So this part of 1 to 3 is known as ingress. Now let's talk about what happens while, like how DMA is involved at the time of output. So for output, suppose there is another buffer. Okay, just for simplicity, think as there is another buffer, and what happens is when the application is generating it, so this our web server process was there, right? So suppose our web server process is there and it has generated a certain output. Okay, and kernel prepares the buffer, it is being written into this one, this particular output buffer. So think it like a output buffer. Now DMA, like here it has read it from here using DMA engine. So DMA engine will be again a sort of a listener on the output buffer side. So the moment something is being written here, what DMA engine will do is DMA engine will again comes in play, DNA and the PCI, and will take this data. So suppose this data was sitting here, it will take this data and then it will send it to the NIC, and then it is NIC's responsibility to send it back to my client browser. So let me clarify one more thing, like there is nothing called output buffer as such. Okay, so output buffer is just like, we can say this is a kernel memory. Okay, this is a kernel memory where the response is being stored before sending. So we can say like this is a kernel memory. This is a kernel memory buffer. Okay, now once this buffer is ready, then the DMA reads it from the DRAM, and send it to the NIC for the transmission. And one more thing, just for our sake of knowledge, before like NIC send it back to the client, before it sends this data back to the client, there are few things it adds, like the Ethernet, TCP, and the IP headers, so that the client has all the data, like where exactly it is coming from. It is very important in terms of the security and the handshaking purpose. So it will generally add the IP headers and stuff. Okay, so this is pretty much how a web server request is traveling across the whole memory layout. And if you understand this whole flow, relations between the descriptor ring, the kernel buffer, the relationship between the SRAM and the DRAM, where TLB will comes in play, translation look aside buffer, and where direct memory access comes in play, everything will be clear to you. And this is pretty much uh, like the huge concepts of the memory management or the memory layout is being packed into a single example. Now, of course, there are other things like page table paging, which we already discussed in our previous videos. So I'm not going in detail into it, like what exactly happens for the around the page table or the paging, and like if there is a huge page is there in the memory, how CPU is going to handle that. That should be pretty clear by now with this whole memory layout discussion. So our key learning in this example is, if the CPU has to manage every byte transfer between the peripherals, it will get bogged down. So what is the solution? The solution is direct memory access. It offloads its work to the DMA controller and the DMA engine, and using DMA controller and the DMA engine, DMA controller plus engine, CPU initiates the transfer, the DMA controller does the work, and CPU gets an interrupt on the completion. And crucial, it is very crucial for this high speed networking and the storage that we see in the modern day computing. Now, after this, let's take one more example to understand further more details, like the relationship between the DRAM and the SRAM and few other concepts on the memory part. Okay, so when we talk about fast memory access, okay, whenever any kind of in distributed system or any kind of computing, whenever we are talking about like we need a system with a very fast memory access, then what is the first database or what is the first system that we often talks about? We often talks about Redis or the memcached. So the properties, basic properties of the Redis is, it is in memory, it is optimized for latency, and it is also like used across very heavily used across all the big techs. So you take name of any of the big tech companies like Amazon, Google, Airbnb, Apple, everybody in some way or another in their like large scale system, they are using Redis in an extensive manner. Okay, used across all the big tech. So that is why we have picked it up to understand it in a little deeper manner. Okay, so now by this time probably we can understand very easily that the Redis in its machine, okay, suppose there is we have a server machine. Okay, in our server machine, what will happen is Redis runs as a process. Okay, so in a machine, Redis runs as a process. Okay, and where it exactly runs, it runs on the like any process, as you know, like any process, it runs on the dynamic RAM side, and any frequently accessed data might go to SRAM. So SRAM is not exactly on the control of the user space program. It is completely OS plus kernel handshaking, I could say. Okay, so when this executable is the Redis executable or the Redis library is running, the executable code as a part of DRAM, what are the things will be there, like the executable code, the internal data structure. So Redis internally uses some kind of a dictionary key value pairs, and actually they uses SS table to be very precise, but like I will just write it like internal DS, for example, dictionary for dictionary. Okay, and there is all the heap allocation and keys and values are being stored in our DRAM. Okay, all these things are being stored in our DRAM. So if you just run a very small experiment, okay, on Redis, you will see a very interesting phenomenon. Okay, so like the first request to my Redis server, the first might probably take 1 millisecond. The second request can take zero point 0.5 millisecond. So why this thing might happen? This thing again, please note my word, this thing might happen. Okay, I'm not saying this will definitely happen. So Redis doesn't directly control what goes into the SRAM. So suppose this is like a first time request. So this is being served from the DRAM. And what happens is from DRAM, Redis, like I will write it here. So I have my DRAM component and also I have my SRAM component. Okay. So suppose the first request that comes, it is being served from DRAM. And once it is being served, it might happen that, again note my word, it might happen that that particular key comes to the SRAM. So next time what Redis will do is, generally, please understand this thing, whenever a request goes, at first always it will check in the SRAM whether it is there or not. Okay, so it will check in the SRAM whether it is there or not. If it is there, then it will return from the SRAM. So from 1 millisecond it might come down to 5 millisecond. So let's write in a formalized way so that it is completely fixed on our brain. So the Redis binary or the process, Redis binary for and the process, whenever we start our Redis server, it will be running on our DRAM. Okay, and then all our Redis key values, it will go to also our DRAM. Okay, so this is basically what happens is, like, Redis have its own malloc function. So when the Redis malloc is being called behind the scene, like when you put, for example, Redis client dot something like Redis client dot set key in your code, so internally this Redis malloc is being called. So I put some key value here, key ABC, and some value as 123. Okay, so then this malloc will be called. Now suppose this ABC might be used multiple times, so I can tell it as a like a Redis hotkeys. Okay, hotkeys means they are frequently being accessed in a very shorter interval of time. Then they might go to SRAM. Okay, and who manages it? This is not which data will go to SRAM. CPU control this. This is very important. Redis has no role into it, so any frequently accessed data is being cached automatically. And also Redis has a very interesting property called disk based snapshot. So what exactly this is, although Redis is a in-memory program, that means like all the operations will be done from RAM, but over the time, for the backing purposes or the backup purposes, what Redis does is Redis takes some data and place it onto the disk. Okay, place it onto the disk, that is the SSD or the HDD. Now uh, in this process what happens is this data will not be put into the DRAM, because this is only for the backup purpose, not for the immediate uh, request serving purposes. So that is why it is being put into the disk. So now probably you understand one implication very clearly, that suppose there is a certain program that is running, how effectively it uses the DRAM, and how operating system control that if it is there are some very frequently accessed data, how things will go to the SRAM. And suppose this have some kind of a memory operations which are not immediately needed, and what happens is they are being put into the SSD or the HDD. So I think now this part is clear. Again, if you take the corollary or if you extend this idea into any kind of video game, suppose your video game has some inherent videos, so those during the run those videos are not exactly required at that very moment. They can be put into your uh, hard disk, and when you see that loading button, what exactly happens is behind the scene it takes those files and bring it to the main memory and show it to you. So that is how this popular systems work. And one of the important aspect also we should touch is how Redis handles the overwrite of the data. So when I say overwrite, suppose this ABC123 you keep on serving from SRAM. Now suddenly one more put request comes. Okay, so this set key I can do for multiple times, right? So now I take this data. So this is happening, and then like for next 2 minutes I'm serving this data, and suddenly another set key request comes. Okay, so when I say another set key means this ABC becomes now 234. Okay, so now from 123 it becomes 234. Now though we cannot serve it from the SRAM. So what happens in that case? Let's understand this thing clearly. So whenever a new key is updated, that key is suppose that key is a frequently accessed one like this ABC, and it is in cache already. One very interesting thing happens. So the cache line, I will just write it over here. Suppose there is this cache line where I have this data ABC, and I'm serving key, and I'm serving the data as 123 from here. Okay, now when there is a write goes into it, a further override goes, then what happens is this cache line, this has been served from the cache, right? This cache line will be marked as a dirty cache. So dirty cache means that there is some data which is updated. Although it is updated, it is not exactly synced with the RAM. So earlier what used to happen is, let me put it here before marking it into the dirty cache. So this cache line, if I just compare, this is completely equal to my main memory. So main memory of course have a copy. So this is my SRAM and this is my DRAM. So main memory has a copy of this data, the same data, ABC and 123. Now what is happening in this case is I am at first writing it to my cache that this has become 234. So now though the first thing that you understand that this is not equal to the main memory, because main memory is now having 123. Main memory is 123 whereas my SRAM is 234. So a program like Redis, what it does is it initially updates or modifies the data that resides in the CPU cache, but that modified data has not been written back to my DRAM, and that is where it is being called as the cache line dirty. Okay, so a dirty cache means it has to be eventually being written back, but now while you are reading this data, try to understand, make a note that this is not the same data which is there in my memory. So this is one of the very important concept of how CPU handles this cache, like the SRAM and the DRAM conjunction. So now the moment this thing happens, there a very important protocol comes in play. Okay, so this protocol is being known as cache coherence protocol. Uh, we will go into a little bit of more detail into it. Okay, so now initially what happens is Redis write the data to the data 1 to 3 into the RAM or into the memory. The CPU then caches that memory write, and it keep on loading the cache. This is like the L1 and L2 cache. From the SRAM, it will keep on getting served to the client. Now the latest value has been 123. Now once it overrides it, there is a cache line dirty that has been marked here. So that means the SRAM and the DRAM is not synced right now, and there comes this thing called cache coherence protocol. So what cache coherence protocol keep on checking is whether this S all the values in SRAM or DRAM are in sync or not. So being the dirty cache, this is again one of the important concept. Being dirty cache, still my data is served from cache only. Ideally, we should name it, like computer engineers are very bad in naming things. It should be dirty RAM because the RAM is not updated, but they named it as dirty cache. But understand these things. Although cache line is being marked as dirty, but cache line served from the cache, this holds the freshest data. Okay, hold the fresh data, and that is why from here, from SRAM only, the data, like when the next get request comes. Okay, so when the next get key request comes, so it will be served from the SRAM only, not from the DRAM. And then once this cache coherence protocol keep on checking that whether this data is actually synced or not, and then what it does is cache coherence protocol does something called write back. And in that write back, it update data into the DRAM. So now the cache line, once this update is complete, the cache line is no longer marked as dirty, and both of them here hold the correct data. Like here is also 234 and here is also 234. So now here probably you understood a very important concept, like how Redis internally uh, handles this dirty cache using cache coherence and uh, dirty cache, and how exactly the cache coherence protocol um, of the operating system makes this SRAM and the DRAM conjunction completely seamless. Now extending this idea into our cloud engineering, suppose you might say that now these days I see that all of the data and all of the systems are already provided by cloud. So now let me ask you a very basic questions. Unless we understand this L1, L2, L3, or the implication of them, suppose we are being given a task to host a Redis process, suppose, okay, in my EC2 server, which EC2 instance or which particular virtual memory I will choose, I will not be able to finalize it even. Why? Because the problem statement is like problem statement in your organization or in a real life, suppose you guess you need to host a Redis instance in some server. Okay. So what will be your deciding factor? Now you know that Redis is a complete in-memory data structure. What your primary concern will be to get the high bandwidth DDR4 or 5 RAM, and there are something called like AWS R series. If you are using AWS as your infrastructure, then AWS R series, which has a good CPU to memory ratio. And only by understanding these concepts in real life we will be able to work with your full cognitive capacity, that uh, this is the kind of a server that I want for my Redis instance or any other web server instance. If it is going to be very memory heavy, then how should I, like, what should be the size and the other details I am going to take. All this design decisions will be influenced by those concepts that we have discussed so far. So that's the video, guys. Like, we have discussed good amount of ground on the memory layout of the program executions, and we touched upon the important concepts of like how the TLB and the DMA and various descriptor rings, kernel interrupt, everything comes together and serves a web request. In that process only we understood the whole memory layout. And then, to understand, like solidify our understanding, we went a little bit internal to Redis. So Redis is like a ocean, like there are too many other things are there, but we kind of understood how this DRAM and SRAM generally comes together and work in a conjunction to serve the uh, the very high throughput traffics. And if needed, this, although Redis is marked as a in-memory data structure, in memory instance, but the disk-based snapshots of this might go to the actual hard disk or the SSD as well. And also, like this cache coherence protocol, write back, and the dirty cache lines, all these things we have explored, and a little bit we touched upon why these concepts are important for our cloud engineering as well. So I hope this has been useful. Please put any question that you have in the comment section. I will try my level best to answer them. Stay awesome.